Nothing's gonna change my world.
Cancel my subscription to the resurrection. Send my credentials to the house of detention. Let me go. Beelzebub has the devil for a attack on me. On me. On me.
Come here, rude boy, boy, can you get it up? Come here, rude boy, boy, just come now, make you a believer.
They say everything's beautiful when it begins. But I was too busy being selfish.
Anytime you listen to music and sounds, I'm sure that you are aware that there are high-pitched sounds and low-pitched sounds, and many sounds in between. Great composers write music that has many pitches, ranging from high to low, and that keeps the music interesting. Many musicians choose their instrument based on the musical range of that instrument. That is, how high or low that instrument will play. One person may like the sound of a tuba, or string bass, while another may be drawn to the higher sounds of a flute or a viola. All of these various pitches are a result of sounds that are different frequencies. So, another way to think of pitch is to think of frequency. If an instrument has a high pitch, then it has a high frequency. If an instrument has a low pitch, then it has a low frequency. But the question remains, frequency of what? And how can it be measured? Well, here is where the science comes in. Sound occurs when air molecules are forced together. After being forced together, they then expand farther apart, creating a wave-like motion of air. Look at the cone of a stereo speaker as it is playing music with a loud beat. Notice how the speaker pushes out with each beat. This compresses air molecules and begins the wave-like motion. Here is another illustration of how it works. Air reacts in a manner that is very similar to water when a pebble is dropped into it, creating a series of waves that move out in a circular motion. Think of the water as the air and the pebble as the sound. The sound waves move out from the sound source in all directions, getting quieter as it gets further and further away. A small pebble can represent a high frequency or high pitch. It creates small waves that are very close together. A large rock can represent low frequencies or low pitches. It creates much larger waves that require much more space to develop. So, we can tell that the speed and the size of a wave relate to that wave's frequency. Also, we have learned that frequency is another term for pitch. But let's dig a little deeper. Let's look at the diagram of a sound wave. This is a diagram of the pitch A. It is the A above middle C on the piano. It is also the pitch that an orchestra traditionally uses to tune the instruments. Orchestras around the world tune their instruments to the pitch A. This is also often referred to as A440. 440 is the number that we're interested in today. Let's listen to the orchestra as it tunes. To unlock the secret of the number 440, let's go back to a diagram of a sound wave. This diagram represents the pitch created by a violin playing the tuning note A440. In order to unlock the secrets of the diagram, we must zoom in on the wave, just as if we were looking at it under a microscope. Now we are looking at a very small portion of that sound wave. We said earlier that sounds are created when molecules of air are forced together. The rise in the wave represents the time that the molecules are forced together. The fall of the wave represents the molecules pushing apart. So, the y-axis is air pressure. You will notice that it happens over and over. This takes time. So the x-axis represents time. One complete vibration of a wave is known as a cycle. And this is how we begin to relate these pitches to numbers. Can you guess how many complete vibrations or cycles an A440 goes through in 1 second? The answer is in the name of the pitch. If you guessed 440 cycles per second, you were absolutely correct. This single vibration actually occurs 440 times in 1 second. This is the wave's frequency, the number of cycles or waves that occur in 1 second. Let's look at how fast that really is. And again, by looking at a perfect wave. This diagram represents a sine wave. It is a perfect wave. Let's listen to it. Notice that there are no imperfections in the shape of the wave, and it is not very pleasing to hear. This represents a pure, single frequency and really doesn't occur naturally on its own in our world. The sine wave was generated by a computer. It is the frequency 220 Hertz, which we discussed in the previous lesson. I have chosen this frequency to use today because it's in the middle of the musical range and many instruments can play this pitch. Let's review the parts of the wave. The high point of the wave represents the place that air molecules are compressed together. The low point in the wave represents the place where they are spaced apart. The y-axis is air pressure. The height of a wave depicts how loud the sound is. Taller waves are louder, shorter waves are quieter. The height or volume of a wave is known as its amplitude. This part of a wave will become very important as we look at the unique qualities of the waves generated by different instruments. If we look at this sine wave in 3D, we see that the only frequency that is represented is 220. There is no amplitude at any other frequency. Now, let's look at the wave that is generated by a cello. Notice that the wave has many more angles and changes than the sine wave. We can see the big portion of the wave moving is at 220, but there are many other changes. What do these represent? Let's take a look at the cello's wave in 3D. Note that there is amplitude represented at a variety of numerical values on the graph. Can you see which frequencies seem to be present? Can you name a few? Is their amplitude the same as the amplitude at 220? Or are they larger or smaller? Note that we are still hearing the pitch A220, but there seem to be other frequencies represented. This is what we call a complex wave. A complex wave is a sound that is made up of many different sine waves coming together to form the unique sound of, in this case, a cello. Notice that there seems to be a frequency at 440, 660, and 880 Hertz. These numbers, which represent pitches, are very important, and they certainly relate to the pitch A220. Do we know anything about any of these frequencies already? Think back to our last lesson on octave relationships. First, the sound is created by changes in air pressure. Second, these changes occur in a wave-like motion. Third, faster waves or frequencies represent high pitches. Slower waves or frequencies represent low pitches. Fourth, one complete vibration of a wave is a cycle. And frequency or pitch is measured in cycles per second. Finally, octave relationships between pitches are represented by a doubling relationship. In Lesson 1, we learned that 440 Hertz and 880 Hertz are higher octaves of the pitch A. Octave relationships are represented by a doubling of any frequency. It is important to note that we don't actually perceive these other frequencies that we see in the graph of the cello's note. But these other frequencies and their amplitudes, or relative volumes, all work together to create the unique sound of every instrument. The frequency that we actually hear is called the fundamental. Note that it is the tallest frequency and the lowest frequency. These other frequencies that show up in a sound wave are known as harmonics. This unique sound of an instrument is also known as its timbre. So, the fundamental and the harmonics that an instrument makes all work together to create its unique sound, or timbre. Let's take a